So today we will start with module 5. Okay, yesterday I already give you the module 4 lecture videos. So I hope that you already watched that video for the module 4. So in the module 5, you will learn about Arithmetic 32 arithmetics and logic operations. So let's look at the, okay, in this module 5 here, you will learn about the AVR instruction that are you going to use it, okay, throughout this course. Okay, so this AVR instruction actually can be divided into 4 broad classes. Okay, so one is for the data movement and memory access. Okay, then we have a data processing, flow control, and system control. Okay, in the next slides, we will learn about all the instruction regarding these 4 broad classes. Okay, so for the data movement and memory access instruction, so this is, okay, to just for recap, okay, so for the data movement and the memory access, okay, we have a few registers, a few input outputs, okay, and then you have a constant data. So this data here is use, okay, you're going to use this data here in order to move from one component to another component. Okay, so okay, here at the middle of this what we call here, this figure here, you know that this is your general purpose register, and then you have a flash, you have a SRAM, you have a IO space, which is your IO's registers, and then you have a constant number and stack. So now you're going to see how to move the data, okay, from the flash to the general purpose register, or from the general purpose register to stack, or from general purpose register to IO space. Okay, let's look at the first one here. Okay, so now we're going to see it from general purpose register to general purpose register, which is from GPR to GPR. Okay, for GPR, to move a data, okay, from GPR to GPR, so you can use this instruction here, okay, MOV and MOVW, which is this MOV is you're going to move a data, okay, from one GPR to another GPR, or copy a data from one GPR to another GPR. Then we have to load a data, okay, from your program memory, okay, which is your flash. This is your program memory. Okay, you can use the program memory. Okay, so you can use the LPM instruction. Okay, which is this LPM instruction stand for load from program memory. Means that you take the value from your program memory, okay, any value from the program memory, and put it to your general purpose register. Okay, so next, in order to move a data, okay, from GPR to your RAM, or from RAM to GPR, okay, we can use this instruction here, okay, to load a data, okay, to load a data from RAM to GPR. You can use either, okay, you can choose from these 3 instructions, which is LD, LDD, and LDS. Okay, in the previous case, we already learned about this thing here. So LDS means that you're going to do we're going to use a direct addressing mode. LD and LDD is by using the indirect addressing mode. Okay, to store a value from GPR to RAM, you can use this instruction. Okay, SKEE, STD, and STS. Okay, so the STS is a direct programming mode, while STD is indirect programming mode. Okay, then we have to move a data from GPR to IO registers. You can either use an in and out instruction. For the IO register, okay, we need to use the IO addresses in order to use this in and out instruction. And if you have a constant value or value from the outside of your CPU, you can use the LDI instruction to load it to your general purpose register. Meanwhile, Okay, if you're using a stack, okay, to move a data from GPR to stack, we can use the push and pop instruction. Okay, push means that we copy a value from GPR and put it to our stack, whilst pop instruction, we store the value from the stack and put it to our GPR. Okay, so this is the what we call the overview lah. Okay, all the data movement and memory access and the instruction that we need to use in order to do the data movement. Okay, so let's look more detail on the instruction for the data movement. Okay, so we have the first instruction here called MOV. Okay, so MOV is used to copy register. Okay, you're going to copy one register value to another register. Okay, so this MOV instruction is used to copy data among the GPR register. Okay, the GPR that you can use is from R0 to R31. Okay, and this is the operation. Okay, RD, and then you see the arrow here. Okay, RR means that you copy the contents of source register and put it to your RD. Okay, and the syntax. Okay, so this is the syntax. MOV RD RR, which is the RR is your source register, while RD is your destination register. Okay, for the operands, okay, your RR and RD can be from R0 to R31. Okay, for example here, okay, you're going to copy the content of R0 to R16. Okay, so means that this is your data memory. Okay, so R0 is on top of your data memory, and then R16 is somewhere around here. Okay, so what you're going to do here is you're going to copy the content from R0, whatever value from R0, and going to put it to R16. Okay, to do that, you can use the MOV R16 R0. Means that you copy the value from this R0 and put it to R16. Okay, and then at the bottom here, okay, you see at the bottom here, this is the status register. Okay, this is your SREG. Okay, and you're going to see what are the flags that are affected every time you execute a certain instruction. Okay, for the MOV instruction, there is no flag affected because this is a data movement. So for the data movement, your flags are not affected at all. Okay, so regarding the CPU cycle, so in order to execute this this instruction here, CPU need 1 clock cycle. Okay, then we have the MOVW. Okay, so MOVW stand for copy register word. Okay, in which you're going to use to copy one register pair into another register pair. Okay, so recall that. Okay, 1 byte is equal to 8 bit, and then 2 bytes is actually equal to 16 bit, which is 2 byte is actually, we can call it as a 1 word. Okay, so means that because now you're going to copy 16-bit value or data to another, okay, we're going to copy 16-bit data from a pair of register and put it to another pair of register. Okay, so the operation, this is the operation here. You see, this is your source register and this is your destination register, which is this is the pair register, and you put it to another pair register of your destination register. Okay, since this is the syntax, MOVW RD plus 1 RD RR plus RR plus, okay, and 1, and then you have a column there, RD. Okay, so what happened here is, let's look at this example. You're going copies the content of R1, R0 into R17 and R16. Okay, so this is your data memory. And this is your R0 and R1. Okay, let's like inside of this R0 and R1, you have a value of FE and 1A, for example. Okay, so you're going to copy this value to R17 and R16. So how to do that? Okay, there are two ways to do that. Okay, the first way here is by using the MOV instruction. Okay, which is you copy 1 byte by 1 byte. Okay, you copy R0 first and put it to R16, and then you copy R1 and put it to R17. Okay, so by using the MOV R16, okay, and get the data from R0, and MOV R17 and get the data from R1. Okay, so this is the first method. Okay, the second way, okay, to do that by using the MOVW instruction, which is we move one word data to a pair of register. Okay, in which, okay, to do that, you just write down MOVW. Okay, what are the destination register? R17, R16, comma, and what is your source register? R1, R0. Okay, and again, okay, because this is a data movement, okay, there is no flag affected, okay, inside of your status register. Okay, then we have the LDI. Okay, so the LDI is stand for the load immediate. Okay, so this one here you already we frequently use in the previous class. So LDIs copy 8-bit data into the general purpose register. So this is the operation and this is the syntax. Okay, since this is involve the immediate value, so your R must be from R16 to R31. Okay, you cannot use from R0 to R15 because this is immediate value. Okay, so I just then we go to LDS. So the LDS also we already covered in the previous class. So LDS stand for load direct from data space. Okay, which is this instruction used to load 1 byte from a memory, okay, data memory, and put it to your register. So this is the operation. Okay, you take the value from memory address, okay, the content from memory address key, and put it to your RD, and the syntax is LDS RD, K. Okay, the operand here RD can be from R0 to R31, while K is your memory, your data memory address size. Okay, for Atmega32, the K is starting from 0000, okay, until 085F. This is for Atmega32. Okay, so for example here, you're going to load the R2 register with a content from this address. So what you're going to do is you just put LDS. Okay, what are the destination register? R2, and from what address that you're going to get the value? From address OXFF00. Okay, again, none of the flags are affected inside of your status register. Okay, for the LDS, you see here, okay, the CPU cycle taken is 2 clock cycles. Okay, to execute this instruction, you need 2 clock cycles. And then we have the LD. Okay, so LD stands for load indirect from data space to register. Okay, so this is it. LD instruction is used to load 1 byte indirect from the data space address to register using pointer register X, Y, and Z. So this is a indirect addressing mode. Okay, so this is the syntax. Okay, we already learned about it in the previous class. Okay, so I just skip this part. Okay, then we have the STS. Okay, so STS stands for store direct to data space. So this instruction is used to store 1 byte from a register to the data space of to your RAM. Okay, so this is the operation. Okay, take the value from source register and put it to your memory addresses. Okay, so the syntax is STSKRR. Your RR can be from R0 to R31, while K is from 0, okay, address 0000 until 085 F for Atmega 32. Okay, again, none of the flags are affected. Okay, and then for this instruction to be executed, it takes 2 clock cycles. Okay, then we have the ST. Okay, ST is stand for store indirect from register to data space. So this is by using the indirect addressing mode. Okay, so you're going to store 1 byte indirect from a register to the data space. So again, this one here, since this is an indirect addressing mode, you're going to use the pointer register X, Y, and Z in order to point to the location that you're going to store. Okay, so as we can see here, okay, you have 3 syntax here. Okay, STX means that your pointer register X doesn't change, while STX plus RR, okay, so this one is a post increment, and ST minus X RR, this is a pre-decrement. Okay, and the status register also not affected. Okay, for the data movement, your status register flags are not affected. Okay, then we have the in instruction. Okay, stand for load an IO location to a register. So the instruction used to load data, okay, from IO space or IO register into your general purpose register. Okay, so this is the operation and this is the syntax. Okay, in RDA. Okay, so this A here refer to your IO address. Okay, previously for the ST, RD small k, okay, this k here refer to data memory address. Okay, so the D can be, your RD can be R0 to R31. Okay, while for A, okay, since you have a 64 IO register, so that's why it started from 0 to 63. D is in decimal lah. Okay, if in hexadecimal from 0 to 3F. So this is the example here in R2516. Means that you're going to read the value from port B and put it to R25. Or you can simply use the register name, which is equivalent to in R25 port B. Okay, which is this one here, you using the register name. Instead of using the IO address, you can use the register name. Okay, then again, none of the flags are affected. And for this instruction here, it takes 1 CPU cycle. Okay, then we have the out instruction. Okay, so this out instruction stands for store register to your IO location. So this instruction used to store from register. Okay, you take a value from your general purpose register and you're going to put it to your IO register or IO space. Okay, so this is the operation. Okay, get the value from RR, source register, and put it to the location of your IO address. Okay, the syntax is out ARR. Okay, your A can be from 0 to 63, while RR is from R0 to R31. Okay, so that's it for the data movement. Any question for the data movement? Okay, for the data movement, we just do the some recaps here. Okay, we go very quickly because we are already done in the previous plus. Ada soalan tak untuk data movement? Do you have any question for the data movement? Okay, if no question, then we go to the data processing. Okay, so for the data processing, there are 4 data process here. One we call it as arithmetic operation, and then we have a logical function, data shifting, and bit operation. Okay, so this arithmetic operation involve the arithmetics such as addition, subtraction, multiplication, division. We doesn't have the instruction for the division. Okay, for the division, we doesn't have that instruction. Okay, while for the logical, it's involved of the logical OR and exclusive OR not. Okay, while the shifting, okay, means that you're going to shift your data either to the left or to the right. Okay, shift data to right or to left. Okay, depending on the instruction that you're going to use lah. And bit operation is the instruction that involve the modification of your bits. Okay, your data bits. Okay, later we will see what are the instructions involved for the bit operation. Okay, so now let's look at the arithmetic operations. Okay, the first arithmetic operation is ADD. Okay, so the ADD stand for add without carry. Okay, you're going to add a 2 register without carries. Okay, you just discard the carry. Even though you have the carry, then by using this instruction, you just discard the carry. So add instruction is used to add 2 registers without the C flags and place the result in the destination register. So this is the operation. Okay, so actually, okay, inside of your instruction set summary, okay, this is your instruction set summary. Okay, as I mentioned previously, okay, you have the instructions column, and then you have an operand column, description, and your operation. Okay, by looking at this operation, you know what this instruction do. Okay, so this is the flags. What are the flags affected? And the number of clock cycles, the CPU cycles. Okay, at the last column here, it shows the number of CPU cycle in order to execute the certain instruction. Okay, so now, okay, let's resume back to this ADD instruction. So this is the syntax, the operation you see here, RD plus RR, and put the result to your RD. Okay, so the syntax here is ADD RD RR. Okay, while your RD can be from R0 to R31, RR also can be from R0 to R31. Okay, for example here, okay, you're going to add R1 and R2 and put the result to R1. How to do that? Okay, you just simply use the ADD instruction, R1 and R2. Okay, means that you know that you're going to add R2 plus R1 and put the result to R1. Okay, if you're going to add R28, okay, if you're going to add to the same register, so just use the ADD. Okay, for example, here you're going to add R28 to itself. Okay, so ADD R28, R28. So what happened here is R28 equal to R28 plus R28. Okay, this one we assume that the content of the register is already there. If the content of the register or value of the register is not there, then you need to load that value first. Okay, that content first. Okay, for the arithmetic operation, there are few flags are affected. Okay, you see here, H flag, S flag, V flag, and Z and C flag. So this is the flag affected every time you do the ADD instruction. Okay, so how many CPU cycles taken? 1 clock cycle. Okay, let's look at the ADD examples. Okay, you're going to show the status of the C, H, and Z flags after the addition of 38 and 2F. Okay, so you have two numbers here, which is 38. You're going to add it with 2F, and then you're going to find out what are the C, H, and Z flags. So how to do that? Okay, so to do that, first, what you're going to do is you need to, since this is a constant number, so this constant number are not inside of your GPR, so you need to load this number to your GPR. Okay, so we can use R16 to load the 38 and R17 to load 2F. Okay, so what instruction that you're going to use? In order to load this value here to your R16, you can use the LDI instruction. So LDI R16 OX38 and LDI R17 OX2F. Okay, so what happens after you execute this line here? So R16 will have 38 and R17 will have 2F. Okay, next. After that, okay, then you add these two numbers here. Okay, you add 38 with 2F. Okay, so you put ADD R16, R17. Means that you're going R16 equal to R16, which is 38 plus with 2F. Okay, since now you are going to find out what are the flag affected. Okay, so in order to figure out what are the flag affected after you execute this ADD instruction here, so what you're going to do is you need to convert, okay, this hexadecimal value to binary numbers. Okay, so R16, which is 38, okay, change it to binary representation. Okay, you will get 0011, and this is 1000. Okay, and then you have our R17. R17 is 2F. Okay, you convert it to binary representation. So this one will become 0010 and 1111. Okay, then you add them up. Okay, 01 you get 1, 01 is 1, 01 is 1, 11 is 0. Okay, then you have a carry there. 11 is 10. Okay, you have another carry. 1 plus 1 plus 1 is 11. You have a carry. 1 plus 0 is 1. And this is a 0. Okay, then you identify what is your C flag. Is there, and what is the C flag? Okay, the carry from bit 7 to bit 8. Is there any carry here? No carry, so you put 0. What about H flag? Okay, H flag you need to refer to bit 3, any carry from bit 3 to bit 4. Okay, since in this example here, you have a carry there. Okay, from after the addition of this number here, you have a carry. So the H flags now become 1. What about Z? Okay, Z we're going to look at the hasil tambah sini. Okay, the result of this addition. Okay, since the result of the addition have value, then what happens? The Z become 0. Okay, if the result of the addition is 0, no values, then the Z become 1. Okay, and then what is the current value of your R16? Can you tell me what is the current value of R16? Because after you do this addition here, okay, the result will be stored to R16. So what is the current value of your R16? Okay, you need to change lah. Okay, change this binary here to hexadecimal. So this one here, 011 is equal to 7. 110 is equal to 6. So R16 now will have 16,
7.
7. Okay, so another example. Okay, you're going to show the status of the C, H, and Z flag after the addition of this 9C and 64. Okay, what are you going to do? Okay, so in order to add these two numbers here, okay, you need to load them to the register, your GPR, and then by using the ADD instruction, then you can add them together. Okay, so now, after you write down this program, okay, so now we are going to find out what are the value, okay, the status of the C, H, and Z flag. So how to do that? Okay, to do that, we're going to change the hexadecimal representation here, the hexadecimal value to binary representation. Okay, so you have a 9C for R20. 9C change to binary, you will get 1001. What is C? C is ABC 12. Okay, so 1100. This is for 9C. Okay, then we have this R21. Okay, so what is the value that you load to R21? 64. So 64 is actually 0110. And then 4 is 0100. Okay, you add them together. 0, 0. Okay, 1, 1 is a 0. 1, 0. 1 plus 1, you get 1, 0. 1 plus 1, you get 1, 0. 1 plus 0 plus 1, you get 1, 0. And this is 1, 0. And this is 1, 0. And you have a carry there. Okay, now you're going to identify what are the C, H, and Z flags. Okay, C flags. Do you have any carry beyond bit 7? So this is your bit 7. This one is your bit 7. Is there any carry beyond the bit 7? Yes, you have a carry. So you put 1. What about H flag? Okay, H flag you need to see at bit 3 and bit 4. Is there any carry from bit 3 to bit 4? Yes, you have a 1 carry there. So you put 1. And what about Z flag? Okay, since the result of this addition is 0, okay, you doesn't have any value here, which is a 0. So the Z becomes 1. Okay, and what are the current value of your R30 at R20? What is the current value of R20? So R20 will have 0, 0, 1, because after you do the addition, you put the result to your R20. Okay, so this is for the ADD instruction. Okay, next we go to ADC. Okay, ADC stands for add with carry. So this instruction is used to add two registers and the content of the C flags and place the result in the destination register. Okay, so let's look at this operation here. You see this operation, RD plus RR plus with the C, okay, and put the result to your RD. So the syntax is ADC RD RR, in which RD and RR can be from R0 to R31. Okay, let's look at this example here. Okay, so this example here actually going to add going to add 16-bit data. Okay, so in order to add a 16-bit data, what you're going to do is, okay, the first, okay, we need to add the lower byte by using the ADD instruction. So ADD R2 R0, and next ADC R31 R1. For example, this 16-bit data, okay, the first 16-bit value is, let's, okay, you put it to, okay, let's something like this. Okay, you have this value here. Okay, so this is the 16-bit value. You're going to add two 16-bit numbers. Okay, 2, 8, 1, 3, for example. Okay, so what you're going to do here is, okay, you need to load these numbers here, okay, to your registers. Okay, before you do any addition, okay, you need to load this number to your register. So how to do that? Okay, first, since this is 16-bit number, so you can divide it into two. One is a low byte, and the other one is a high byte. So 6, 7, you put it to R0, for example, and this one you put it to R1. Okay, since LDI cannot use the R0 and R1, so we just change this one. Okay, so this one we put it to R20 lah. Okay, and this is R21. What about this one here? Okay, this one you put it to R16. Yeah, R16. So this one you can put it to R17. Okay, so to add this 16-bit number, so for the lower byte, okay, we can use the ADD instruction. Okay, you add this number, and somehow, after you do this addition, sometimes it will produce a carry. Okay, after you add these two low byte number, and it will produce a carry. So what happened here? For the higher byte, okay, you need to use the ADC instruction. Okay, that's why, okay, to add two 16-bit number, what you're going to do is here is you use the ADD for the lower byte. Okay, in this case, ADD R20, R16, and higher byte ADC R21, R17. Okay, so this is what happened in the example lah. Okay, for the low byte, use the ADD instruction, while higher byte, you use the ADC. Why? Because sometimes when you add the lower byte, it will produce a carry. So this carry here, you need to take to account for the, okay, you need to include in your higher byte addition. Okay, so this is the flags affected. Okay, you have some flag affected here, which is half carry, sign number, overflow, negative, 0, and carry flag. Okay, what about the CPU cycle? Okay, the CPU cycle for this instruction is 1 clock cycle. Okay, let's look at this ADC example. Okay, you are going to write a program to add two 16-bit number. Okay, you're going to write add two 16-bit number, which is the number is 3CE7H. Okay, you have E3 EC37H. Okay, H. This H is represent the hexadecimal number with 3-bit 8D. Okay, 3-bit 8D. Okay, you're going to add this number here. Okay, assume that R1 already have the 8D. Okay, so this one is already have a, okay, you put 8D to R1 already inside the R1, and R2 is already inside the 3B already inside R2, while 37, oh sorry, E7, yeah, not 37, E7. Okay, so E7 already inside R3, and EC is inside R4. Okay, then place the sum in R3 and R4. Okay, so after you add the addition, you need to put the sum to R4 and R3. Okay, so R3 should have the lower byte. Okay, so this is a lower byte and this is a high byte. Okay, since this is a 16-bit number, you can divide it into two, one for the lower and one for the high. Okay, for the lower byte, what instruction that you're going to use? You're going to use the ADD instruction, while for the high byte, we are going to use the ADC instruction. Okay, so how to do the programming to add these two numbers here? You just simply add the lower byte first. Okay, ADD R3 R1. Okay, why R3, R1? Because the result you're going to store inside R3. Okay, if you use the ADD R1, R3, then it is wrong. Okay, why? Because the result now put to R1, which is wrong lah. Okay, in this question here, it asks you to put the result to your R3. Okay, then after you finish this one here, then you add with your higher by using the ADC instruction. So ADC R4 with R2. So this is the programming that you need to write in order to add these two 16-bit numbers. Okay, any question up until here? Okay, if no question, then we go to the ADIW. Okay, so ADIW stands for add immediate to word. Okay, you're going to add immediate data to a 16-bit number. Okay, so this instruction is used to add immediate value, which is the value must be from 0 to 63 only, to a register pairs. Okay, since this is a 60-bit, so you need one register pairs, and place the result in the register pairs. Okay, so this is the operation RD plus 1 RD equal to RD plus 1 RD plus with K. Okay, in which your K is from your K is from 0 to 63 only. Okay, and this is the syntax ADIW RD plus 1 RD, comma, K. And the operand for the RD is only valid for R24, R26, R28, and R30. Okay, means that if you choose the R24, so the register pair for R24 is R25 because D is D plus 1. So RD is 24, so RD plus 1 is 25. If you choose the R26, then the register pair is R27. Okay, for example here. Okay, you're going to add 1 to R25, R24. Okay. You're going to add with 1. So how to do that? Okay, by using the ADIW. Okay, so just use the ADIW R25, R24, and with what number? So since this is an immediate, so you can directly put the immediate value 1. Okay, so you put 1, add 1 with this R25 and R24. Okay, next, you're going to add 63. Okay, this is a decimal number to the Z pointer register. Okay, okay, you have a Z pointer register. Now you're going to add with 63. So how to do that? Just simply write ADIW. Okay, what are your Z pointer registers? So Z pointer register is actually a combination of R31 and R30. So you just put ADIW R31 R30, and with what immediate value number? 63. Just like that. Okay, so for this one here, okay, the flag that are affected only S, V, and Z, and C. How about the clock cycle? It taken 2 clock cycle in order to execute the ADIW instruction. Okay, for another example here. Okay, so you're going to add 26. Okay, you have a 2 numbers here. Okay, which is 5313. Okay, you're going to add with 26. Okay, so this 26 is in decimal, not hexadecimal. So how to do that? Okay, first, you need to load this number to your register pair. Okay, so in this case here, we load it to R30 and R31. Okay, once you have already load the value, Okay, sorry, this is not hexadecimal, yeah. Okay, this is what we call here decimal number. Okay, so now what you're going to do after that is after you load the number to your ZL and ZH, and then after that you can use the ADIW instruction, okay, to add with 26. Okay, that is for the ADIW. Okay, next is for the subtraction. Okay, the second arithmetic operation we have is subtraction. So for the subtraction, we have a few instruction for the subtraction. One of them is subtract without carry. Okay, so SUB stand for subtract without carry. So this instruction used to subtract two register and place the result in the destination register. So this is the operation and this is the syntax. Okay, what about the GPR? What are the GPR that can be used for this instruction? Okay, you can use from R0 to R31 for both RD and RR. Okay, so this is the flags affected here. Okay, H, S, V, N, Z, and C. Okay, let's look at this example here. Okay, so now what you're going to do here is going to subtract, okay, 3F minus with 23. So how to do that? Okay, first, this 3F and 23, you need to put it to your GPR. Okay, in this case, let's this one we use the R21, put it to R21, and this one we put it to R20. Okay, and then you write down the program. So LDI R20 with OX23 and LDI R21 with OX3F. Okay, now by looking at this operation here, you're going to subtract 30F minus with 23. So the R21, okay, should be your destination register. Okay, so R21, R20. Okay, and then we have the SUBI. Okay, SUBI stand for subtract immediate. Okay, you're going to subtract a register with an immediate number. Okay, for the addition, there is no add with immediate value unless you use the ADIW. Okay, but for the subtract, we can subtract register with immediate data. Okay, so SUBI used to subtract a register with a constant value and place the result to your register state destination. Okay, so this is our operation. RD equal to RD minus K. K is your immediate value, your constant value, which is from 0 to 255 in decimal, or 0 to FF in hexadecimal, or 0 to 1111111 time if you use the binary number. Okay, since this is involve the immediate value, okay, you see here the instruction is ended with an I, so the R must be from R16 to R31 only. Okay, so this is the affected registers as the affected flag inside of your status register. And let's look at the SUBI example. Okay, you're going to write a program to subtract 18 from 29. Okay, you have a 29, you're going to subtract it with 18 and store the result to R21. Okay, okay, you have two ways to do this. Okay, A without using SUBI and B by using the SUBI instruction. So how to do that? Okay, let's look at the without using the SUBI. Okay, you're going to subtract this number here and put it to R21. Okay, so by right, the bigger here, okay, the biggest number, okay, or the left number here, you need to put it to your R21. Why? Because at the end, you need to put the result to your R21. Okay, what about this one here? 18. Okay, the 18 you can put to any register lah. Okay, which is you can use the R16 for example. Okay, so now what you're going to do, you need to load this number first to the registers, and after that, by using the SUB instruction, then you can subtract these numbers. Okay, so LDI R21 with 0x29 and LDI R18, sorry, R16, yeah, we're using the R16 with OX18. Okay, then after that, we use the SUB, okay, R21, comma, R16. What happened here? So here is R21 equal to R21 minus with R16, which is equivalent to 29 minus with 18. This is without using the SUBI instruction. What about if you're going to use the SUBI instruction? Okay, for the SUBI instruction, only the first, okay, numbers, you put it to your register, while the second number, you just make it as an immediate value. Okay, so in this case here, we need to put this number, 29, put it to R21. Why R21? Because at the end, we're going to put the result to R21. So LDI R21 with OX29. And then by using the SUBI R21 with what value? OX18. So what happened here? R21 equal to R21 minus with 18. Okay, so this is for the SUBI instruction. Okay, next is SBIW, okay, which is subtract immediate from word. Okay, so the SBIW used to subtract immediate value. Okay, the value must be from 0 to 63 from a register pair and place the result in the next register pair. Okay, so since this is a word, means that the size of the data is 16-bit, so that's why you need to have one register pair. Okay, so this is the operation and this is the syntax. Okay, so again, this one is similar to the ADIW, which is your RD must be from R24, R26, R28, and R30 only. While K should be from 0 to 63 only. Okay, so this is the example for SBIW, and this is, okay, the flag affected after you execute this instruction is R, S, V, N, Z, and C, and this instruction takes 2 clock cycles to execute. Okay, let's look at the examples down here. Okay, you're going to write a program to subtract 2917 minus with 18. Okay, and store the result to R25 and R24. So how to write that program? Okay, first, what you're going to do is, okay, since this is a 16-bit number, okay, the first number is a 16-bit number, then you need to divide it to low byte and high byte. So this is your low byte and this is your high byte. Okay, and then it's telling you that you need to store the result to R25 and R24. So this is R25 and this is okay, this is R24 and this is R25. Okay, so next, what are you going to do? Okay, so these numbers here, you need to load to your register, your general purpose register. Why? Because the SBIW telling that, okay, you need to have one register pair minus with the immediate value. So you need to put 2917 to one, okay, to one register pair, and after that you minus with 18. Okay, so in this case, R29 you put it to R20. Oh, sorry, 29 you put it to R25, while 17 you put it to R24. Okay, so by using the LDI instruction, okay, LDI R24 OX17, and then after that you can use the SPIW R25 R24, and then okay, subtract with immediate data, which is OX18. Okay, so that is for the SBIW. Okay, next we have the SBC. Okay, so SBC actually a subtract with carry. Okay, so this instruction used to subtract two registers and subtract it with the carry flags and place the result to the destination register. So this is the operation RD equal to RD minus RR minus with C. Syntax SBC RD RR. Your operand RD and RR can be from R0 to R31. Okay, let's look at this SBC example. Okay, you're going to write a program to subtract two 60-bit number. Okay, you have two 60-bit number, 2762. You're going to minus with 1296. Okay, assume that, okay, it tells you that R26 already have 62. Okay, so this one already inside the R26. And 27 already inside R27. Okay, and place the difference in R26 and R27. Okay, so the result need to be placed in R26 and R27, in which R27 will be the lower byte. Okay, so since this is a 16-bit number, so what you're going to do is you divide it by 2. One is for the low byte and the other one for the higher byte. Okay, so for the subtract, lower byte similar to addition. Okay, this one you can use the SUB instruction. While for the higher byte, we need to use the SBC. Why SBC? Can you tell me why we need to use the SBC for the higher byte? What is the reason?
Because we will put the carry in the higher part.
Okay, correct. Because sometimes, okay, if you do the low byte subtraction, you need to borrow from the higher byte. Okay, since this one here, you see here, the top here is smaller than like the bottom here. Okay, the top number is smaller than bottom. So what happens is you need to borrow from your higher byte. So that's why we need to use the SBC. Okay, means that we need to what we call here to borrow from the higher. So that's why we need to involve the carry flags. Okay, during for the higher byte. Okay, next what you're going to do is before we write the programming. Okay, so these numbers here already inside the R26 and R27. What about this one? 96 and 12. Okay, this number here not yet inside of your register. So you need to put this 96 and 12 to your GPR. So let's look this one. We just put it to R16, and this one we put it to R17. Okay, now we write down the what we call here the program. Okay, so LDI R16 with value 96 and LDI R17 with value 1, 2. Okay, so now this value 96 and 1, 2 already inside your R16 and R17. Okay, then after that, we use the SUB. Okay, we subtract the lower byte first, and then after that, followed by the higher byte by using the SUB. Okay, subtract R26, R16. So SUB R26, R16, and SBC R27, R17. Okay, so this is how you're going to write a program in order to subtract two 16-bit numbers. Okay, we go to the previous slides. Okay, for this example here. Okay, so previously we using the SBIW. Okay, this is one of the method lah. Okay, the second method you can also use the SUB and SUBI. SBC. So how to do that? Okay, since this one here, okay, because this is involves 16-bit number, so why not the 18 here? Okay, also you make it as a 16-bit numbers. Okay, so now your 18 now, if you make it as a 16-bit number, it becomes 0018. Okay, so what happened here? This one you put it to R16, and this one you put it to R17. Okay, for the lower byte, you use the SUB. For the higher byte, you use the SBC. So what happened? Okay, you load all the value here first, and after that you can, okay, so all the value you can write up here, and then you use the SUB R24, R16, and SBC R25, R70. So this is the second solution. Okay, the first solution is by using this one because this is by using the solution you only need 3 lines of instruction. But by using this solution here, you need 4, 5, 6 line of instruction. Okay, which is your program become longer compared to the first solution. Okay, next, SBCI. Okay, so SBCI stand for subtract immediate with a carry. Okay, so SBCI instruction is used to subtract a content from a register and subtract it with the C flag and place the result in the destination register. So this is the operation here. RD equal to RD minus K minus C. Syntax is SBCI RD K. Okay, so we go back to the previous example. Okay, how can you tell me how to reduce this program here? Anyone? Can you tell me how to reduce this program? Okay, now you use it. You have a 4 line of programming in order to subtract this number here. So how to reduce it so that it becomes shorter? Anyone?
Do both subtractions in the same step?
Okay. Mana tadi? Okay, just now with okay, this one. Okay, so how are we going to reduce this instruction so that the program become shorter? Okay, so this one here, okay, we already learned about the SUBI and SBCI. Okay, why not? Okay, previously we used the SUB and SBC, correct? So why not the lower byte? Okay, we use the SUBI, and the higher byte we use the SBCI. Okay, previously, okay, this one here, we already learned about SUBI, which is to subtract with an immediate, and then we have another instruction called SBCI, which is subtract immediate with a carry. Why not we change from SUB using the SUBI and SBC by using the SBCI. Okay, if you use this instruction here, what happens is you no longer need to load to R16 and R17. Okay, this value no longer need to load to your R16 or and R70. Why? Because you can make it as a immediate data. Okay, so to do that, okay, you simply write SUBI, okay, R26, okay, so R26, and with what number here? 96. And SBCI R27 with what value? 1, 2. Okay, so now you reduce this program, okay, from 4 lines of instruction to 2 lines of instruction only. Okay, any question up until here? Okay, we finished the addition and subtraction. Okay, next we are going to see the multiplication. Any question, guys?
Doctor, just a general question about like registers. If we perform an operation on them before we set the value, does the operation assume that it has 0 set, or does it give us an error?
Means that you not put the value inside the register, is it?
Yeah.
Okay, if you not put the value inside the register, then how you going? Then by default the value is 0. Okay, because the data memory is a volatile memory. Okay, by right, every time you switch off your microprocessor, what happens is all the value inside of your data memory, your GPR, your RAM will erase to 0, become 0.
So it doesn't give an error. It gives it uses it as if it's a 0.
Yeah, yes, no error.
Okay, thank you.
Okay, next we go to MUL. Okay, MUL stands for multiplication. Okay, so we have a few MUL instructions. Okay, one is the MUL, and then we have the MULS and MULSU. Okay, so these 3 instructions is used for the multiplication or multiply. Okay, so let's look at the first instruction of the multiplication. Okay, so MUL stands for multiply unsigned number. Okay, so every time you use the MUL means that you're going to multiply between 2 unsigned number. Okay, so this instruction perform 8-bit by 8-bit, and it will produce 60-bit of unsigned numbers. Okay, so this is your destination register multiply with source register, and the result will be 60-bit of unsigned number, because this is an unsigned number multiplied with unsigned number, you will produce a 60-bit of unsigned number. But okay, this result will be stored inside of R1 and R0. Okay, every time you use the multiply, the result will be stored inside of R1 and R0. Okay, the operation here, RD multiply with RR, okay, and the result will be stored inside R1, R0. So the syntax is MULRDRR, in which RD and RR can be from R31, R0 to R31. Okay, for the MUL instruction, only 2 flags affected, which is Z and carry flag. Okay, then we have the MULS. Okay, later we will see the example how the multiplication works. Okay, so MULS stand for multiply sign number. Okay, so MULS instruction perform 8-bit multiply with 8-bit and produce a 16-bit sign number. Okay, so again, if you looking at this operation here, okay, RD multiply with RR, the result will be stored inside of R1 and R0. Because why? Because it will produce 60-bit number. So 60-bit number, you need to have one pair of register. Okay, so this is the syntax. MULS, RD, and RR. Okay, but okay, for the MULS, the operand of your RD and RR must be from R16 to R31. Okay, again, only two flags affected, which is Z and C flags. And last but not least, okay, before that, okay, so now because this one here it is involved the sign number. Okay, before we go more detail on the MULS, MULSU, now we are going to see what is a signed and unsigned number. Okay, because the multiplication will involve the signed and unsigned number. So you need to know how to determine this value is signed number and this value is unsigned number. Okay, so in signed 8-bit operation, okay, bit 7, okay, which is the most significant bit, will be your signed number, while D0 to bit 0 to bit 6 are the magnitude. Okay, you have a 8-bit data. Okay, so this is a bit 0, 1, 2, 3, 4, 5, 6, and 7. Okay, so this bit 7 will become your signed number. Okay, while bit 0 to bit 6, this is your magnitude. Okay, the value of your numbers. Okay, if the bit 7 is 0, then the value here is in positive number. Okay, means okay, the range of positive number are from 0 to 1 to 7. Okay, if the positive number larger than 1 to 7, then you need to use the 16-bit operand. Okay, you need to have the 16-bit number. Okay, if the bit 7 here is 1, then what happens? You know that this one is a negative number. So the magnitude here, okay, the magnitude inside here, the value inside here, you need to change it to second complement in order to get the real number, the real value. Okay, so let's look how the AVR would represent the signed number. Okay, now let's look at this example. So how -5 will be represented in AVR. Okay, you have -5. So what the -5 value will looks like in AVR. Okay, first thing first, what you're going to do is, okay, first we get the value of 5. Okay, we take the positive 5, okay, and get the binary representation for positive 5, okay, by using the multiply the weightage, or you can press the calculator. Okay, so I just put the multiply the weightage. So 1, 2, 4, 8, 16, 32, 64, and 1 to 8. Okay, and then 5 is actually is 4 plus 1. Okay, you get a 5. Okay, the rest you just put 0. So this is the binary representation for positive 5. Okay, then we have the negative number. So how this value, you're going to change it to the negative number. Okay, to change it to negative number, you need to do second complement. Okay, there are two ways to do a second complement. Okay, first is the longer way, and the second is the shortest way. Okay, let's look at the longer way. Okay, so you have the 0, 0, 0, 0, 0, 1, 0, 1. So the first step, what you're going to do here is you do, okay, get the first complement. Okay, you invert each of this bit here. Okay, to get a first complement, you need to invert all of this bit. Okay, so that's it becomes 0, 1, 0, 1, 1, 1, 1, and 1. Okay, and then to change it to the second complement, you need to add with 1. Okay, so you add with 1. 0 plus 1, you get 1, and the rest is. Okay, so this is the longer way lah. Okay, then you get the second complement. Okay, which is this number here will represent negative 5. Okay, the shortest way, okay, so you have the 0, 0, 0, 0, 0, 1, 0, 1. Okay, you traverse from right to the left. Okay, find the first one. Okay, this is the first one. So what happened? You copy this number. What about the rest? The rest you just invert them. Okay, so now they become 1, 0, 1, 1, 1, 1, 1. Okay, so see, the value are similar. Okay, so this is how you're going to, this is how the AVR would represent negative numbers. Okay, if you change this one here, okay, this binary to hexa, okay, so the value will be F8421, 8 plus 2 is 10, 11, 11 is B, so FB. So FB actually is negative 5. Okay, if you assign okay, so this is for the signed numbers. Okay, so let's look at another example. Okay, show how the AVR would represent negative 34. Okay, negative 34 ish. Okay, so how to do that? Okay, first, okay, you need to get what are the binary representation for 34. Okay, so 34 by using the 8. Okay, because this is a hexadecimal, so you can use the 8421 method. Okay, to get the binary representation. Okay, 34 is 0, 0, 1, 1. This is for 3. All 4 is 0, 1, 0, 0. Okay, this is for 3, 4. And then you're going to make it as negative. So how to do that? By using the second complement. Okay, by doing the second complement. How to get a second complement? Okay, we just use the shortest way. Okay, traverse from right to the left. Find the first one. So this is your first one. So what you're going to do? You just copy back whatever value before you see the first one, and then what about the value after that? Okay, this value here you need to do. Okay, you need to invert them. Okay, so now it becomes 1, 0, 0, 1, 1. So this is the binary representation for negative 3, 4, which is equivalent to 8, 4 is actually 12, 12 is ABC. Okay, CC. Okay, CC is equivalent to negative 3, 4 each. Okay, so this is the how we are going to find out the sign representation for the negative number inside AVR. Any question? Okay, if no question, then we go to another instruction, which is MULSU. Okay, so this is the third instruction. Okay, so MULSU is actually multiply sign with an unsigned number. Okay, similar to what we similar to the previous instruction. Okay, so it perform a 8-bit multiply bit with 8-bit and produce 60-bit multiplication of signed and unsigned number. And all the result will be stored inside R1 and R0. So R1, so this is the operation RD multiply with RR. You put the result to R1 and R0. And this is the syntax. Okay, for the MULSU, okay, you need to use register from R16 to R23 only. Okay, cannot use other than that. Okay, if you use other register, then this error will occur. Okay, and this one here, two flag affected, which is Z and C. Okay, next we have the INC instruction. Okay, so INC stand for increment. So this instruction used to add 1 to the content of register RD and place the result in the destination register RD. So this is the operation RD plus 1 and put it to your RD. What about the syntax? INC RD. Okay, you see that this one here, increment RD only involve of one register. So this is data direct register mode. Okay, addressing mode address. Okay, and then operand here is from R0 to R31. Let's say like you're going to increment your R22. How to do that? Okay, you can simply write increment R22. Okay, you have two ways to do that. Okay, one is the shortest way to increment. Okay, increase R22 by 1. Okay, so how to do that? The first one here, you just use the INC instruction. So it's then what happened? You already increase your R22 equal to R22 by 1. Or the second method here, okay, you can use the ADD instruction. Okay, so what you're going to do is, okay, sorry, LDI R21 with 1, okay, because we want to increment by 1, and then after that ADD R22 with R21. Okay, so this is only one line of instruction, but this one you need two lines of instruction. Okay, the flag affected for the increment are S, V, Z, and C only. Okay, then we have a DEC. Okay, DEC stands for the decrement. Okay, so this decrement used to subtract 1 to the content of the register and place the result in the destination register. So this is the operation RD equal to RD minus 1. Syntax is DEC RD. So the operand here is RD can be from R0 to R31. If you're going to subtract your what we call here. Okay, let's we put an example here. Okay, subtract R22 by 3. Okay, how to do that? Okay, you can use the DEC instruction, okay, which is you subtract R22 first time and then subtract again. Okay, now for the second time, okay, if you're going to minus with 3, then you need to subtract by using the same instruction 3 times. Okay, so this is how you're going to do in order to subtract R32 minus with 3. Okay, you call the DEC 3 times. Okay, again, this is the flags affected. Okay, no need to memorize what are the flags affected because this one here you can refer to your instruction set summary. Okay, any question up until here? Ada soalan tak?
No, doctor.
Okay, no. Great. Okay, so if no question, then we go to the next data processing operation, which is a logic operation. Okay, so for the logic operation, we have a few instructions involved. One of them is logical AND, okay, which is A and D. Okay, so this logical AND perform the logical AND between the content of the RD and RR and place the result in the destination register. So this is the operation here. Okay, RD dot RR. Okay, the dot here means that you're going to do the logical and put the result to your RD. Okay, syntax is AND RD RR and operand is D is the operand. Okay, so for the AND, okay, what you're going to do here is you need to memorize, okay, recall back the truth table of logical and so this is A, B, and F. Okay, the truth table of logical and is 0, 0, 0, 1, 1, 0, and 1, 1. So what happens if both input are 0, the output of F will be 0, and 0, 1 also you get 0, 1, 0, the output will be 0, and 1, 1, the output will be 1. Okay, for the logical AND, you can summarize it. Whenever the input, one of the input is 0, then the output will be 0. And when both input are 1, then the output will be 1. Okay. Okay, for this one here, the flag factor is S, V, N, and V. Okay. And V always 0. So every time you use do the logical AND, the V always 0. Excuse me, can I take a 2 or 3 minutes breaks?
Yes, doctor.
Okay, load I R16 OXA2 and load I R17 OXF0, and you're going to do the A and D R16 R17. Okay, so now what you're going to do here is, okay, so what happens after you execute this line here, your R16 will have this value A2, while this one here, R17, will have F0. Okay, so to do the logical AND, what you're going to do here is you need to change them to binary numbers. Okay, by using the 8 4 to 1 method, okay, you change them to binary numbers. So this is A actually is a 10. So 1 0 1 0. What about 2 is a 0 0 1 0. And F is actually as a 1 1 1 1 15, and you have a 0 0 0 0. Okay, now you're going to the logical and put the result to R16. So what happened here? Okay, so we check bit by bit, okay, and do the logical AND operation. Okay, 0 and with 0, you will get 0. 1 0, you get 0. 0 0 is 0. 0 0 0. 1 0 is 0. 1 1, you get 1. 1 0 is 0. 1 0, you get 1. Okay, so the current result here is A0. So what happened here? R16 now have A0. So this is how the logical AND do. Okay. Next, okay, we have the next instruction is ANDI. So logical AND with a immediate value. So ANDI instruction perform the logical AND between the contents of register RT and a constant, place the result in the destination register. So this is our operation. Okay. Again, you see the rd.k. You know that you're going to, okay, you're going to what we call here, you're going to do a logical AND with the immediate value and put it to your destination register. So this is the syntax. And while since this one here is involved the immediate value, which is the instruction is ended with I, so the destination register must be from R16 to R31. Okay, and the flag affected, only four flags are affected, which is sign number, negative, and 0, while V always 0. Okay, so let's look at the examples here. Okay, now assume that, okay, this instruction is executed sequentially. Okay, then we have A and DI R17 with value 2, 214, for example. Okay, so what happened? Okay, so now what is the current value of R17? So this is your R17. Okay, your R17, the value is remains, no change to R17, which is 1111 0000. Okay, what about 214? Okay, since this one here doesn't have any what we call here any symbol in front of this symbol, in front of this number, so you know that this number belong to decimal number. So you need to change it to binary number. So how to do that? Okay, you can simply press the calculator. Can somebody help me? What is the binary representation for 214? Two, 1, 4.
110.
Okay, 110.
101.
101 and 10.
Yes.
Okay, so this is 214 and this is your F0. Okay, so what you're going to do? So again, you do the logic AND for each of these bit here. So 0 with 0, you get 0, 0, 1 is 0. This is also 0, 0, 1 with 1, you get 1, 1, 0, you get 0, 1, 1 is 1, 1, 1 is 1. Okay, and then you change the number, okay, this binary to hexagon number, so you get 88421, which is 12 plus 8 plus 4 is 12, plus 1 is 13. 13 is A, B, C, D. Okay, so the value will be D0. Okay, so this is what how to perform the logical AND DI, which is you perform the logical AND with an immediate value. Okay, next we look at the OR. Okay, so OR stand for logical OR. Okay, so this instruction perform the logical OR between the content of register RD and register RR. Place the result in the destination register RD. So this is our operation here. RD. Okay, every time you see this symbol here, you know that you're going to perform a logical OR and put the result to your RD. This is the syntax and this is the operands. Okay, so what about the flag that affected after you execute this instruction? Okay, only 4 flag affected, which is S, V, N, and Z. Okay, now we look at the examples. Okay, so you have OR R17 with R16. Can we do that? Nothing change. Okay, if you do the okay, wait. Or R16. Okay, so R16 with R17. Okay, I just swap the position. Okay, so you're going to OR R16 with R17 and put the result back to R16. Okay, what are the current value of R16? So this is your R16, A0. Okay, so A0 is 1010 0000, and then R17 is D0. So this is your D0 and this is your A0. So what you're going to do? You're going to do a logical OR. Okay, so before that, you need to remember lah what is the truth table for the logical OR, which is this is AB, this is your input, and this is your output. If AB is 0, 0, the output will be 0. 0, 1, it is 1. 1, 0 is 1. 1, 1 is 1. So you know that if one of the, you can conclude that one, if one of the inputs is 1, then the output will be 1. If both output are 0, then the output will be 0. Okay, so based on this here, okay, so you just compare the D0 and A0, do the logical OR, so you get, okay, so 1, 0, you get 1. 1, 0 is 1. 1, 0 is 1, and 1, 1 is 1. So now you get back F0. So R16 now will have new value, which is F0. Okay, then we have the ORI. Okay, so ORI stand for logical OR with immediate. Okay, so this ORI instruction perform the logical OR between the contents of the RT and a constant and place the result in the destination RT. Okay, so this is the operation. This is the syntax, and bear in mind that since this is involved the immediate value, so your operand must, your destination register must be from R0 to R31. Okay, let's look at this another example for this one. Okay, the next one is ORI R17 with 0B 0010 1011, for example. Okay, so what is the current value of R17? Okay, by looking at this, the current value of R17 is still D0. Okay, so this is a D0, 1101 0000. And now you're going to you're going to do a logical OR with an immediate value. So this immediate value is in binary numbers. Okay, since it is in binary numbers, so no need to convert them lah. Okay, so you can simply take the number and do the comparison. Okay, do the logical OR. So this is a 0010 and 1011. So what happened? Okay, so you do the logical. So 01 you get 1, 01 is 1, 00 is 0, this is a 1. And what about this one here? So this is a 1, 1, 1, and 1. Okay, so the final value here is F. 8, 4, 2, 1. So 8 plus 2 is 10. 10 plus 1 is 11. 11 is B. Okay, so the R17 now will have new value, which is F. B. Okay. Next, we looked at the last one here. Okay, before we stop, we looked at the last one here, exclusive OR, EOR instruction. Okay, so the EOR instruction perform the logical exclusive OR between the content of RT and RR register, place the result to RT. So this is the symbol, this is the operation of exclusive OR, which is, you see, every time you see this symbol here, you know that you're going to do the logical OR, RT, put the exclusive OR with RR, put the result in RD. So this is the syntax. The operand of here is what we call here. Okay, so this is the operand is for RD and RR is can be from R0 to R31. Okay, and we'll see the what we call here. Okay, before that, okay, we need to know lah. Okay, before we do this, what we call here, any logical exclusive OR. Okay, so let's say lah this one. Okay, I put another register like LDI R18 0x24, for example. Okay, so now, and then exclusive EOR R18 R17. Okay, so now before we do this instruction here, okay, what happened here is after you execute LDI R1824, so R18 now will have a new value 24, and then you're going to do the exclusive OR. So before we go do the exclusive OR, we need to know the truth table of exclusive OR. So this is A, B, and F. What happened when 0, 0? What is the output of the exclusive OR for 0, 0? Okay, is it okay? 0, 0, 1?
1.
1, 1, 0 is 1, 1, 1 is 0. Okay, if you don't remember, okay, the truth table of exclusive OR, you can simply write the expression of exclusive OR, which is A exclusive OR with B, which is equivalent to A bar B plus A B bar. Okay, then you put this value here inside here, and then you can come out with the output. Okay, so now R18 is 24. So this is R18. Okay, I just put here. 24 is 0, 0, 1, 0 and 0, 1, 0, 0. What about R17? Okay, R17 is FB. Okay, 1, 1, 1, 1 and 1, 0, 1, 1. Okay, now you're going to do the exclusive OR by referring to this table here. Okay, you do the exclusive OR. So 0, 1, you get 1. 0, 1 is 1. 1, 0 is also 1. 1, 0 is 1. 1, 0 is 1. What about 1, 1? 1, 1, we get 0. And this is a 1 and 1. So the final answer of R18 now will have a new value, which is 8 plus 4 is 12. 12 plus 1 is 13. 13 is A, B, C, D. Okay, D, F. Okay, so this is the final value of your R18. So any question up until here? Okay, next week we will continue with one complement, negates, and etc. Okay, if no question, then I think we can stop here. Thank you guys and see you next week.
Thank you, Doctor.